Hi, in this video we are going to talk about the coin change problem, so let's get started. The problem is about given a set of coins and we are going to store it in a one-dimensional array called V. For example, we will have coin 1, coin 2 and coin 3, for example $1, $2 and $3. And given an M amount or total, for example $5, and the question is how many ways the coins V can be combined in order to get the total M. It's very important that the order of coins doesn't matter. And this is the so-called coin change problem. We are going to talk about a concrete example and illustration of this problem, so it will be clear. So for example, we have some coins and we are going to store it in the array V 1, 2, 3, and we have the total amount, so M is equal to 4, and the solution to the coin change problem is equal to 1, 2, 3, 4. We have 4 possible ways of doing it. For example, 1, 1, 1, 1, 1, 1, 2, 1, 3, and 2, 2. It's very important that the order of coins doesn't matter. For example, the 1, 3 is equal to 3, 1. And I'm not sure, I don't want to repeat myself over and over again, just to make sure that the problem is clear, that here we talk about, for example, dollars, and the M is equal to $4, and we have $1, $2, and $3 coins. And so the solution is we can construct, for example, the $4 out of 4 $1 coin, and so on. We could use $2 coin and so on. So the first approach is to use recursion. The naive approach is to use a simple recursive method or function. For every single coin we have 2 options, whether to include it in our solution or exclude it. There are 2 main problems. First of all, there is overlapping subproblems, and it's very important then if it turns out that there are overlapping subproblems, it is a good hint to use dynamic programming, because otherwise we would recalculate the same problems over and over again. About the time complexity is exponential, although 2 to the power of n, where n is the number of coins. And it's quite easy to see it because for every coin we have 2 options, whether to take it or not. And we have n number of coins, so that's why the complexity will be exponential. So a better solution would be to use dynamic programming. We have to create a solution matrix and have to use memoization. And that's why we create this DP table, stands for dynamic programming table. The first index represents the rows, the second index represents the columns. We will have num of coins plus 1 rows and total amount plus 1 columns. So we have to define the base cases. If the total amount is equal to 0, there is one way to make the change. If the number of coins is equal to 0, there is 0 way to change the amount. It's very important that instead of the exponential time complexity, it will have the complexity order V times M, where the V is the coins, 1, 2, 3 and so on. The M is the possible values of the total amount, 0, 1, 2, 3, 4 and so on. So we have to check if the coin value is less than or equal to the amount needed. If yes, then we will find ways by including that coin and excluding that coin. If we include the coin, then we reduce the amount by coin value and use the subproblem solution. So we have to subtract VI from total amount. If we exclude the coin, then the solution for the same amount without considering that coin would be a better solution. This is very important. This is the formula we are looking for. How can we calculate the DP table values with the I row and the j column? It is 0 if I is equal to 0, which means that it is the first row. So the first row consists of zeros. If the j is equal to 0, it means that this is the first column. So the first column consists of 1s. And otherwise, if the vi is less than or equal to j, then the dp table ij is equal to the dp table I minus 1j plus dp table ij minus vi minus 1. It is just a formula, we are going to use it, and I hope that it will be clear. And otherwise the vi is greater than j, then we have to use the formula dp table I minus 1 and j. Okay, so let's see a concrete example. The m, or the total amount, is equal to 4, for example $4, and we want to calculate that how many possible ways we can make it if we have the v one-dimensional array storing coins 1, 2, and 3. So we are going to create m plus 1, so 5 number of columns, and number of rows will be the v.length, which is equal to the size of the array. Because it consists of 3 items, it will be 3 plus 1 is equal to 4. So we are going to create this table with from 0, 1, 2, 3, 4, representing the totals. So the column header is equal to the totals. The row headers are equal to the coins. And because we want to find subproblems, we consider the totals 0, 1, 2, 3, 4 step by step when we can have 0, 1, 2, 3 coins at the same time. We solve the subproblems and combine them for the final solution. So we consider the fact that what about if the m, so the total amount, is equal to 0? Then we solve this subproblem. It is just a subproblem because we know that the m is equal to 4. So it's kind of nonsense to calculate it, but this is how dynamic programming works. We keep constructing subproblems because these subproblems are very easy to compute. And with the help of the subproblems, we are able to solve the whole problem easily. The m equals 1 means that we assume the total amount to be 1. What would be the optimal solution if m would be 1? Then m is equal to 2. What would be the optimal solution if the m would be 2? m3 and m4, it is the final step. That was the optimal solution when the m is equal to 4, and that's what we are looking for. And the same is true for the coins. First of all, we consider that what would be the optimal solution if we take no coins at all. Okay, that's why the first row is equal to 0. It's kind of a nonsense. Well, what would be then the second row? Is very important. We can solve the problem that what would be the optimal solution if we could take only one coin, the first coin. Then the third row. In the third row, we're trying to find the answer of what would be the optimal solution if we would take the first 2 items, the $1 and the $2, and then the third row, so we can take all of them, the 1, 2, 3. So these are the subproblems. It's very important to get a good grasp of dynamic programming, that we keep constructing subproblems. Why is it good? Because solving subproblems are very easy, and we store it in a table like this, and this is called the so-called memorization. And we just have to look it up, and it's going to be very fast. Okay, of course, the first row is going to be equal to 0. This is, by the way, if you carefully watch this equation, you see that the dp table ij is equal to 0. If the I is equal to 0, it means that the first row is going to be equal 0. The first column is going to equal 1, according to this equation, and then we go grid by grid and trying to find a solution. So assume that the m is equal to 1, so the total amount is 1, and we can consider a single coin, the first coin. And how many possibilities are there? Of course, a single possibility, because we have a one coin, a $1, and we try to make $1. Okay, we just have to take it. What would be the solution if m would be 2 and we have the ones? And because the order doesn't matter, it is going to be the same and the same and the same one. You can use this formula, by the way, but it's quite intuitive to fill it with ones. Here it's going to be a bit tricky, so that's why we are going to use the formula. So what does this formula mean simply? If the given vi is greater than the j, the v, if you may recall, stores the coins. So the v1, for example, is 1, the v2 is 2, the v3 is 3, so the v is just the coins. So if the vi is greater than the j, and the I is the row index, 0, 1, 2, 3, and the j is the column index, 0, 1, 2, 3, 4, then copy the content of the box above the current one, and else the dp table ij is equal to the value of the box above the current one plus the value in the same row, and we have to go to the left as many steps as the number of the coin. So for example, if we considered $1, then we have to take one step to the left. If we consider the second item of our coin array, it is the $2, so we have to take 2 steps to the left. Then $3, 3 steps to the left, and so on. If you get a good grasp of this, it's going to be very easy to compute this table. So it's going to be 1, because if you may recall that in this situation, the vi, which is 2, it is greater than the j, which is 1. The j is equal to 1. That's the column index. The vi, we have to look up. The I is equal to 2 because it's the second row. So what's the second item of the v array? It is 2. And because 2 is greater than j, we have to copy the value of the box above the current one. And the box above the current one is the red, above is 1. Okay, the next one. Here we have to use the first formula because vi is less than or equal to j. The vi is equal to 2 because it's the second item in the v array. The j is equal to 2, so we have to use the dp table I minus 1j plus the dp table I j minus vi minus 1, which is going to be equal to the dp table 1, 2, and the 1, 2 is equal to 1, plus the dp table 2, 0, which is going to be equal 1, and 1 plus 1 is equal to 2. And what about this? We just have to use this formula, and it's going to be very easy. Yeah. So, because 2 is less than 3, we have to use the first row of the dp table ij formula, and we have to add the box above the current one, which is 1, and we have to take as many steps to the left as the index of the row, and the index of the row is just the first, this 2. So we have to take 2 steps to the left, and there's a 1, so 1 plus 1 is again 2. And again, because the vi is less than or equal to j, we have to use the first row in our formula, and we have to add the 1 plus 2, which is going to be equal 3. Then we go to the next row. In the next row, the index, the I, is equal to 3, and in this situation, the j is equal to 1. So the 3 is less than 1, so the vi is less than j. So we just have to copy the value from the box above. There's a 1, we just copy it again. 3 is greater than 2, so we have to copy again. 3 is equal to 3, 3 is j, 3 is the I, and the vi is equal to 3. So we have to use the first line in our dp table ij formula. So we have to add the box above, 2, plus we have to take 3 steps to the left. Why 3? Because we are at the third row. It is the third item in our v array. So 1, yeah, that's a 1, and we have to add 2 plus 1. It's going to be equal 3. Of course, you can use this formula. It's quite mechanic. You just have to substitute the values, and you just have to add them together. Then we have to use again this formula because the vi is less than j. So 3 plus 1 is equal to 4. And this is the value we are looking for. So we have solved our problem without recalculating the same problems over and over again. In the next video, we are going to implement both the naive algorithm and the dynamic programming approach, and we are going to compare the two. And if, for example, such small problems, it is going to be okay. But for example, if the m is equal to 1000, and for example, in the V array we have 1, 2, 3, 4, 5, with the help of dynamic programming, you are going to solve this problem very fast. But with the help of recursion, without dynamic programming, it is going to break. For example, my machine has broke down because it's calculated so many subproblems over and over again and wasn't able to get to the end. So that's all about the introduction to dynamic programming and coin change problem. Thanks for watching.